Assalamu alaikum students. I hope all of you are doing great. In this video, I am going to cover jointly Gaussian random variables which are very important as they are used in almost every area of science and engineering. So let us start. Two random variables x and y, they are said to be jointly Gaussian random variables if their density function or joint density function is represented by this expression, that is fxy of x comma y is equal to 1 over 2 pi sigma x sigma y under root 1 minus rho square into e raised to power minus 1 over 2 into 1 minus rho square into x minus x bar whole square divided by sigma x square. The sigma x square is variance, whereas this x bar is the average value of random variable x minus 2 rho x minus x bar y minus y bar whole divided by standard deviation of x and standard deviation of y plus y minus y bar whole square divided by variance of random variable y. So this is the expression of jointly random variable x and y which are jointly Gaussian. These jointly Gaussian random variables are sometimes known as bivariate Gaussians. If you try to sketch it, its density function will look like this. And in z axis this is fxy of x comma y. Here if you cut this curve with a plane which is parallel to xy plane, then the intersection will be an ellipse. Here this will be sigma y and the other axis will be sigma x. These are the spread or standard deviations in respective axes. If sigma x and sigma y are equal, then this ellipse will be a circle. Moreover, the maximum point, maximum of this curve will appear at x bar and y bar. If you put the value of x bar in x here, here, and y bar here and here, you will get the maximum magnitude of this joint Gaussian density function. Here, as it is clear that when you put x bar here, this term will be 0, and when you put x bar and y bar here, this term will also be equal to 0, and when you put y bar here, this term will also be 0. So this 0 multiplied by this 0, then this whole term will be e raised to power 0, which is equal to 1. So the maximum of this joint Gaussian density function is equal to fxy of x comma y is equal to this thing, which is equal to 1 over 2 pi sigma x sigma y under root 1 minus rho square. Moreover, the density function at x bar y bar at this point, it has a maximum value, which means it will always be greater than or equal to fx of x comma y. Now let's suppose here this correlation coefficient rho is equal to 0, which means both random variables x and y are uncorrelated. If this rho is equal to 0 and both random variables x and y are uncorrelated, let us put rho in this expression of jointly Gaussian random variables. What we will get is we will have fx of x comma y is equal to 1 over 2 pi sigma x sigma y. Here if we put 0, then what we will get is we will have 1 into e raised to power. Here I am putting this rho square is equal to 0, because this rho is equal to 0, then we will have here minus 1 by 2 into x minus x bar whole square divided by sigma x square minus this whole thing will be 0 because this rho is equal to 0 plus y minus y bar whole square divided by sigma y square. So let me rearrange this expression. What we will get is we will have, I can write this expression, the denominator as 2 pi whole square under root into sigma x square under root into sigma y square under root. I can represent the denominator of this fraction as this thing, because this square will be cancelled with square root. Here the sigma x square, this square and this square will be cancelled with the square root into e raised to power minus 1 by 2 x minus x bar whole square divided by sigma x square minus 1 by 2. I am multiplying this 1 by 2 with both these terms. Here I will have y minus y bar whole square divided by sigma y square. Now I can split this term into two terms as 1 over under root 2 pi sigma x square into e raised to power minus 1 by 2 x minus x bar whole square divided by sigma x square into the second term, which is 1 over under root 2 pi sigma y square. If you multiply this term with this term, you will get this term. And I am also splitting this term, which is for x random variable I have this term, whereas for y random variable what I will have is e raised to power minus 1 by 2 y minus y bar whole square divided by sigma y square. So if you observe it, this is the density function of random variable x, which is Gaussian, whereas this is the density function of random variable y, and it is also Gaussian. Y minus y bar whole square divided by 2 sigma y square. So you can conclude that this joint density function is equal to the marginal density function of random variable x as well as the marginal density function of random variable y, when the rho is equal to 0 or correlation coefficient is equal to 0. Here this is jointly Gaussian random variable, whereas this fx of x is a Gaussian random variable and this fy of y is another Gaussian random variable. Moreover, as you can see from here, if this expression is satisfied, then both random variables x and y are independent. So we can say if two random variables are uncorrelated, as we have initially assumed, then they are also independent. This relationship is only valid for Gaussian random variables. Whereas for other random variables, you cannot say anything about independence if you know about the correlation coefficient. If you know two random variables are uncorrelated, you cannot say anything about independence. But for Gaussian random variables, if two random variables are uncorrelated, they will always be independent. This is only true for Gaussian random variable. That means for Gaussian random variables, if two random variables are independent, they will be uncorrelated. If for Gaussian random variable, two random variables are uncorrelated, they will also be independent. This is only true for Gaussian random variables. Now let's suppose you have n random variables x1, x2, xn, and they will be jointly Gaussian if their density function is equal to fx1, x2 up to xn of x1, x2, xn is equal to determinant with exponent 1 by 2 and the determinant of covariance matrix inverse divided by 2 pi raised to power n by 2 into e raised to power minus x bar cx inverse and x minus x bar. Here we have transpose divided by 2. Here this x minus x bar is a vector which can be represented as x minus x1 bar, x2 minus x2 bar up to xn minus x n bar. Whereas this is a covariance matrix and it is equal to C11. This is a covariance between x1 and x1. Here we have C12, which is a covariance between x1 and x2, and up to C1n. And here we have C21, C22, C2n up to Cn1, Cn2, Cnn. Here this Cij is defined as expected value of xi minus xi bar into xj minus xj bar, which is equal to sigma xi square for all I is equal to j, and it is equal to cxi xj for all I is not equal to j. So for n random variables x1, x2 up to xn, they will be jointly Gaussian if the density function or joint density function is equal to this expression, where this is covariance matrix which is given here, whereas this x is a vector in which all the random variables are given, and this Cij can be defined as with this expectation in which if I is equal to j, you have variance of random variable, and if they are different, you have covariance between random variable xi and xj. Now let us check this expression or evaluate this expression for n is equal to 2. Now for n is equal to 2, the covariance matrix will be equal to C11, C12, C21 and C22. As clear from this expression, this C11 will be equal to sigma x1 square, whereas the C22 will be equal to sigma x2 square. Now come to the C12. Now the C12 can be defined as expected value of x1 minus x1 bar into x2 minus x2 bar. So let us multiply and divide this covariance C12 with sigma x1 and sigma x2 and sigma x1, sigma x2. I am multiplying and dividing this covariance with sigma x1 and sigma x2. This is sigma x2. So this whole term is equal to the correlation coefficient between x1 and x2 into this standard deviations sigma x1 and sigma x2 is equal to C12. Let me repeat, this covariance between random variable x1 and x2 is defined as expectation of x1 minus x1 bar into x2 minus x2 bar. I am multiplying and dividing this term with sigma x1 and sigma x2. So this whole term, this term is known as correlation coefficient, whereas the sigma x1 and sigma x2 are given here. So the C12 is equal to this thing, and I am writing this term here, which is sigma x1 and sigma x2. Similarly, you can write here sigma x2, sigma x1. This is the covariance matrix for jointly Gaussian random variables for n is equal to 2. Now what we need is, we have this thing. Now we need to determine its inverse. To calculate the inverse of this 2 by 2 matrix, first you need to determine its determinant, which can be calculated as Cx determinant is equal to sigma x1 square sigma x2 square minus rho square into sigma x1 square sigma x2 square. This rho square into sigma x1 square and sigma x2 square. Now taking common sigma x1 square and sigma x2 square, what you will get is 1 minus rho square into sigma x1 square and sigma x2 square. This is the determinant of this covariance matrix. Now the inverse of 2 by 2 matrix is equal to 1 over determinant of this covariance matrix into adjoint of this covariance matrix. So as I have already determined the determinant of this covariance matrix, which is equal to 1 minus rho square into sigma x1 square sigma x2 square into adjoint of Cx, which you can easily find from here. These terms will be interchanged. Here you will get sigma x2 square, and here you will get sigma x1 square, whereas these terms will have negative sign with them. So here you have minus rho sigma x1 sigma x2 sigma x2, whereas here you have rho into sigma x1 sigma x2. Now this Cx inverse will be equal to, I am taking this term inside this matrix, then if you multiply this term with this sigma x2 square, this sigma x2 square and this sigma x2 square will be cancelled, and the remaining term will be 1 minus rho square into 1 over sigma x1 square. Here you will have minus rho over sigma x1 sigma x2, because this sigma x1 and sigma x2 will be cancelled from this sigma x1 and sigma x2, whereas here you will have minus rho over sigma x1 sigma x2, and here you will have 1 over sigma x2 square. This is the inverse of your covariance matrix. Now one more thing that you need is, you need to determine the determinant of this inverse matrix. It is required. So let us calculate the determinant of this inverse matrix. Before calculating the determinant of this inverse matrix, let me further simplify it. Here you will have 1 over 1 minus rho square into sigma x1 square. Here you will have minus rho over sigma x1 sigma x2 into 1 minus rho square, and here you will have minus rho over sigma x1 sigma x2 into 1 minus rho square, and here you will have 1 over 1 minus rho square into sigma x2 square. Now if you calculate the determinant of this matrix, what you will have is Cx inverse determinant is equal to product of this diagonal entries, which will be equal to 1 over 1 minus rho square whole square into sigma x1 square into sigma x2 square minus product of this anti-diagonal entries, and it will be equal to rho square divided by sigma x1 square sigma x2 square into 1 minus rho square whole square, and it will be equal to 1 minus rho square divided by 1 minus rho square whole square sigma x1 square sigma x2 square. So this term will be cancelled and you will have determinant of this covariance inverse matrix equals 1 over sigma x1 square sigma x2 square into 1 minus rho square. So this is the determinant of covariance inverse matrix. Now as we have calculated that determinant of covariance inverse matrix, as well as we have also calculated the covariance inverse matrix. So let us put the values inside this jointly Gaussian random variables for n is equal to 2, and let's see what we have. So here we will have x1 x2 of x1 and x2 equals this thing which we have here, which is equal to 1 over sigma x1 square sigma x2 square into 1 minus rho square whole raised to power 1 by 2 divided by 2 pi 2 by 2, because here we have n is equal to 2 into e raised to power this whole thing. And let me express this whole expression with letter a. Now let us calculate this a, which will be equal to minus 1 by 2, this is minus 1 by 2 into row vector, which is x1 minus x1 bar and x2 minus x2 bar into this covariance matrix inverse matrix into column vector x1 minus x1 bar and x2 minus x2 bar. Now if you solve this matrices, what you will get is this a will be equal to minus 1 by 2 into 1 minus rho square into x1 minus x1 bar whole square divided by sigma x1 square minus 2 rho x1 minus x1 bar into x2 minus x2 bar whole divided by sigma x1 and sigma x2 plus x2 minus x2 bar over sigma x2 square, this is whole square. So after solving these matrices you will get this term. Now we need to put this a in this equation, what you will get is this squares will be cancelled with the square root, whereas you will get under root here, whereas 2 by 2 is equal to 1, and here we have calculated this expression which is our a. The result will be equal to f x1 x2 of x1 x2 is equal to minus 1 over 2 pi sigma x1 sigma x2 under root 1 minus rho square into e raised to power minus 1 over 2 into 1 minus rho square into x1 minus x1 bar whole square divided by sigma x1 square minus 2 rho x1 minus x1 bar x2 minus x2 bar whole divided by sigma x1 sigma x2 plus x2 minus x2 bar whole square divided by sigma x2 whole square. So this is the expression of jointly Gaussian random variable in which we have two random variables x1 and x2. Now if you compare this expression with this expression that we have discussed in the start of this video, here if you replace this x1 with x and x2 with y in this expression, you will get this expression. They are same. Please make one correction, this is plus 1. Here we have minus. So this is end of the topic. If you have any question, please feel free to ask me via my email ID or you can comment below. See you in the next video. Thank you very much.